Hello everyone, I'm Hongyu, and I'm honored to be the first student presenting paper review this semester. And I'm also very excited to talk about the paper of my first choice, multiplying matrices without multiplying. First, let me talk about the reasons why I chose this paper in the first place. And the first reason is that it has a catchy title. And research has shown the more attractive your title is, the more likely your paper is going to be cited. Right? For example, thinking inside the box, I always faster than a CPU, things happen, and also attention is all you need. Actually, this paper relates to my research interest, which is building systems for large machine learning models. The question here is that why machine learning models are so hard to scale. So if we look inside most of the machine learning methods, they are nothing but a bunch of matrix multiplications. Right? For example, ranging from simple multivariate linear regression to PCA or to large deep neural networks. And in this case, for example, the MIT transformer model. And at its core is the so-called attention mechanism. And in the corner, we can see there are a bunch of different kinds of matrices. And they are all methods people have come up with over the past 5 years to really scale up the matrix computation. And people use sparsity and approximation and break and break, all kinds of techniques, just to avoid the complexity in both space and compute to power the input size out. Okay. So exact matrix multiplication can be quite expensive. People have come up with techniques to approximately compute the result. Right? These methods are called approximate matrix multiplication, or AMM. And compared to the proposed method in this paper, they are not as efficient. So the proposed method in this paper can achieve 100x speed up compared to exact matrix multiplication, and 10x speed up over the existing AMM methods. And as Tommaso has said, that's one of the interesting features of this method is that it requires no addition and multiplication operations when one of the matrices is known ahead of time. So before we delve into detail how they achieve this speed up, let's first look at existing AMM methods, right? How they approximately compute the matrix multiplication. So the main idea is to use so-called a linear projection, right? And to introduce some sparsity into the matrix. And say we want to compute matrix A and B, they are dense matrices, and the ultimate goal is to bound the error by the original matrix multiplication. So for example, we have complicated matrix A and B, and they are dense, right? And instead of computing A and B exactly, so what do we do? Well, we first introduce a matrix pi A and a matrix pi B. And we use these two matrices to sample or specify the original matrices respectively. Okay. And so by computing the product, pi A and pi B, we get A hat and B hat, which are lower dimensional, and also which requires less memory and also less compute. In this case, we can recover the multiplication exactly. This is a simple example, but just to give more intuition as to how existing AMM methods are doing. Okay. So the main approach proposed in this method is twofold. Okay? So the authors use so-called product quantization augmented by locality-sensitive hashing to do the matrix multiplication. And we will talk about each of them later in detail. And the objective here is exactly the same as we had in the AMM methods, where we want to bound the error, the approximation, by the original product of A and B. And in this case, what we want is to learn three functions. The encoding function of A, the table construction function of H, right, B, and then the aggregation function F. And to be clear, these two functions are not linear. Okay? They are not the linear projections that we had as we had in existing AMM methods. And they are learned, and we'll see how the learning process goes. So before I introduce the method, I'd like to touch upon the assumptions this paper makes. Okay. The first assumption is, well, we assume that matrix A and B both fit into a single device. Okay. And also, apart from the matrix A we're going for, we also have a training matrix A prime. Right? In machine learning term is that we not only have the test set we want to make predictions for, but we also have a test set, a training set, sorry. And also for both matrix A prime and A, they are skinny and they are tall matrices, and all matrices are dense. So in machine learning term, this is called the over-parameterization, where we have more parameters, or more data points, sorry, than number of parameters in our model. Okay, so before I delve into product quantization, I'd like to pause here to see if there are any questions, urgent questions. Okay. So the goal of product quantization is to compress the data matrix A into an approximation, but of a lower dimension. So the first step in this process is to learn a set of so-called prototypes. So what are those things? So say we have the data matrix A. What we do is we first partition the matrix A, transpose of the matrix A into subspaces or subarrays vertically. Okay, we don't touch the horizontal dimension here. And in this case, we partition into 2 subspaces for each row, right? Then what we do is that we conduct a k-means on each of the subspaces. In this case, the k equals to 3. We learn 3 so-called prototypes, those waves, as approximations of each of these subspaces, A1, A11, A12, etc. Okay. Then what we do is that we use the function g, to encode the original space to a set of indices. So this is quite a busy figure. Let me introduce in detail. So the data vector A, you can think of it as the one row of the data matrix, capital A. Okay? This is one row, and what we have is we partition this vector into 3 subspaces. Okay? And what we do, for each subspace, we have, in this case, 1, 4 prototypes. So in this case, what we have is a 4x3 table of prototypes. And what we do is that we select the best approximation for each subspace, comparing with the original data vector. So in this case, the square, the triangle seems to be the best approximation of the first subspace. And yeah, the sinusoid wave seems to be the best approximation of the original data. And we note down the index of the corresponding prototype in our table, right? And we do this for all subspaces. Now, having encoded the data matrix, what do we do next is we deal with the B matrix, right? So-called the Poiret vector. The B matrix is a column of the the B vector is a column of the capital B matrix. Right? In this case, we'll also partition the original space into the same number of subspaces. And what we do next is to compute this element-wise or Einstein product between this original data vector, not the Poiret vector, with the corresponding prototypes. So in this case, for the subspace, the first subspace, we'll compute for every single one of the prototypes, all the results. We note down all the results in the table. And we do the same for the second column, and we note down the dot products, and so on and so forth. So now what we've done is we pre-computed all the dot products in our table. So we store them in our memory for those dot products. And now when it comes to multiplication, when it comes to the actual computation, what we do is that we have the encoded data vector, right? We have a set of indices, and we also have a table of a table of dot products. So what we do, we take the indices, we look up the table, we note down, we look up the results, and we use the aggregation function f to get the final result. So this process requires no multiply addition operation.
I have to ask you a question in between. If you say you have a piece of a vector, and the prototype for this piece is this triangle, okay?
Yeah.
That means that the values in this vector have a shape like this. Is that how I need to understand?
Thanks
Meaning
for
that the values first get larger and then smaller? Is that what it is, or something else?
No, actually, sorry for the emoji. Actually, so these are vectors, still vectors, and these symbols, those waves can be replaced by anything. Like this is just a symbol of the original matrix, and what they are computing is computing the numerical value of the matrix. So it's a nonlinear projection. So the comparison is not necessarily one-to-one in this case. So these waves can be replaced by any emojis, if you like. So they are not exactly like these linear waves. They are comparing the waves. So this is just an analog, if you like, of the vector space. Any further questions? Okay. So to summarize, what we have during the training phase is that we learn prototypes, right? We learn prototypes for each subspace, and we construct a lookup table for all the dot products for each of the prototypes with the so-called query vector, the B matrix. And during the training or the test inference phase, where we have a new A prime data vector, what do we do the same. We do the same encoding process for A prime. We go from GA and we index or we encode A by selecting the best approximations of the prototypes, and we note down the indices. And during the multiplication process, we just look up the results directly and we aggregate the results. So this process requires no multiply add operation, but instead lookup add operation. So I understand that this still can be a bit complicated because it was quite hard for me to understand what's going on. So I'd like to give more intuitions by doing something I've never done before, which is do a live demo. Specifically, I'd like to first quantize the vector A of 12 dimensions to 4 dimensions, and then we select the best prototypes by pairwise Euclidean distance, and then we reconstruct the original A matrix using those prototypes. Is this running? Yes. So in this case, what we have a vector of x, right? You can think of this x as a raw of the transpose A. And the dimension is 12, and we want to partition this x vector into 4 subspaces. Right? So in this case, we have 4 subarrays. And for each subarray, the dimension is 3. The next step, what we want is to do k-means, or to find centroids as the approximation. So in this case, what we have is that we want to have, in total, 32 prototypes. And for each subspace, we have 8 prototypes. And then what we do is that we want to create prototypes for each subspace. We just loop through all the subspaces. I'm using the notation from the paper, so the C, and then for each the vector, for each the subspace, we learn a prototype. We learn 8 prototypes. In this case, I'm not learning anything, but just using random numbers as an illustration. So for the original subspace, for the first subspace, what do we have? Is we have 8 vectors, right? 8 prototypes.
Sorry, is that K?
Sorry?
Is 8 K? I mean, is K 8 in this case?
Sorry, are you asking what the K is? Or?
Yeah.
Yes, so the K is the number of prototypes for each subspace. Yeah. So in this case, we have total 32 for 4 subspaces. Each has 8 prototypes. And so essentially, what C is a tensor of prototypes, right? We have 4 subspaces. For each subspace, we have 8 prototypes. For each prototype, each prototype has a dimension of 3. Now we define the Euclidean distance, and to use Euclidean distance for each prototype, we find the best prototype for each subspace. And essentially, what we are doing is that we are compressing the original X to just for indices into that prototype table. Now, by using this for indices, what we can do is we can approximately reconstruct the original data X. And as we can see, the Euclidean distance between the original data and, this is the original data, and this is the approximation. We have a Euclidean distance of approximately 6. It is not the best approximation in the world because we're using, we're not learning anything. We're using random vectors to approximate the original subspaces. Okay, so this is just to give a brief intuition as to what exactly is happening in this product conversation. Now, at this point, maybe who can tell me what would be the bottleneck in these 3 steps?
Finding the prototype.
Finding the prototype. That's exactly correct. Yes. So yes, the bottleneck is finding the best prototype. Exactly. And this is because we have, for example, we have constructed the matrix P, the set of prototypes, and we have constructed from the prototypes and the query matrix B a tensor of the results. But in order to look up into the results, we need to compare. We need to select the best prototypes using the traditional ways to use a pairwise Euclidean distance. And this is where locality-sensitive hashing comes into play. And the authors propose a novel method using locality-sensitive hashing with the help of binary regression tree to do this lookup or to do this selection. So before I move on to locality-sensitive hashing, any questions at this point? So before we talk about like this fancy algorithm, let's first look at what LSH, how LSH compares to a normal hashing. Right? So in a normal hashing algorithm, what we want is to minimize the collision rate. So in this case, we have human faces and pumpkin faces. Although these 2 pairs look the same, but still they're different. So we want to hash them to different pockets. Right? But in LSH, what we want is to maximize the collision rate between similar items. And in this case, we want to hash the human faces into a bucket and the pumpkin faces into another bucket. So, but one quick note here is that traditional LSH methods are an iterative process, okay, because it has very high false positive rate. We need to hash this space again and again. And this is not applicable in our case because we can't tell the aggregation function, hold on a minute, I need to hash the space again to reduce the false positive rate. So this is why the authors used the binary regression tree, which has a linear, logarithmic complexity, and also it comes with very natural theoretical guarantee bounds for the errors, and it can exploit the training set we have to learn a set of parameters for later use. And also we can use SIMD to do parallel lookups. So let's go through a quick example as to how this process is going, okay, how the algorithms actually looks like. So in this case, we have a subspace of a row of the original matrix, right? And we say the subspace or the subvector, I remember the subvectors, called X, right? So the first step in this process is to select heuristically 4 sets of indices to evaluate. And the number of indices in each set depends on the level we're evaluating at on the tree. So the second step is to use the corresponding indices. For example, at level T, we want to use the set of indices JT at node I, right? And we decide which branch we should go next, right? To the left one or the right branch. So we do this hashing all the way down to the left, and as a final step, we aggregate all the prototypes that has been trained and hashed into the libs during the training process. We aggregate, we average all the prototypes as the best approximation as the original space. And in this case, the level is bounded by 4, and we have maximally 16 libs for SIMD operation. Okay. So there are also a bunch of other optimizations. For example, the authors also proposed ways to improve prototypes, to minimize construction loss, and to improve the aggregation function. But for more details, if you are interested, then please look in the paper. So this is one of the most interesting results in the evaluation section. And on the x-axis, what we have is the speed up of the exact matrix multiplication. And on the y-axis is the accuracy. The task here is a softmax classifier on 2 data sets, CFR10 and CFR100. And the 2 data points I'm highlighting here are the exact matrix multiplication. So they are on the right left corner, and they achieve the best performance, but the speed is the baseline of the baselines. Now what we're looking at is so-called the scalar quantize. Scalar quantize is linear quantization. So we don't learn fancy functions, we just do linear quantization, linear projections, and this is how far we can get. And now we're looking at the grid dots, the grid lines, are pretty much at a Pareto frontier already. So they are using sparsity to do approximate matrix multiplication. And still, although they are very good, still compared to the red dots, which are the results of this paper, they're still quite slow. And because the x-axis is on a log scale, the results from this paper can really achieve 100x speed up without much performance degradation. So over the past weeks, I've also been tweaking the code. So this is one of the results I've got from their code. And so this is on the CFR100 dataset, and on a very skinny matrix, and over 3 runs. I haven't noted down the hardware because I was having some trouble with installing dependencies on M1 chip. So this is results from a virtual machine on the cloud. But essentially, we're using only one thread. So in this case, what we're looking at on the leftmost corner, what we're looking at is the exact multiplication and scalar quantization. And on the x-axis, we have number of operations in million scale. On the y-axis, we have the accuracy. Right? I'm interested in how much trade-off between the number of operations it can achieve, how much operations the method has to carry out in order to gain a certain accuracy. Right? In this case, the exact multiplication and the scalar quantization, they're not reducing the multiplication, the number of operations. So they achieve the best results with the same number of, approximately the same number of operations. And the green axis, the green crosses, are the sparsity. So as we increase the number of operations, they converge to the best performance possible. And this is the code name of this work in their code. And by their method, we can achieve quite good accuracy by just slightly increase the number of operations conducted.
What are the different red dots? What's the difference between all the red dots in the rectangle?
Yeah, that's a good question. So I should point out is that I should point out is that some methods are deterministic. So the speed up for each point, for example, scalar quantization, we know for each task how much speed up it can achieve. But for other methods, for example, the sparsity and the proposed method in this work, it has a range. It depends on how the prototype is learned and what kind of matrices we'll encounter. So in this data set, we have a bunch of matrices, and the performance vary between each run. And also, I also slightly increased the number of operations, and this method very quickly achieves good performance.
How do you increase the number of operations? Which parameter are you changing there in the method?
Yeah, so they expose the number of operations as in one of their functions. So once they have achieved a certain operation, they stop the increasing. They have a certain threshold in their code. Yeah. Thank you for the questions.
Is there an explanation for what type of matrices it's not working as well as far as?
Sorry, come again.
So is there, because for some matrices it's not working as well as for others, right?
Yes, that's true. Yeah, that's a good question. I don't think they have explained for what edge cases this performance will degrade.
And on the slide before, why is there such a big difference between CSAIL 10 and CSAIL 100?
This one.
This one? Yeah, so the papers performance is dropping for CSAIL 100 for 10. So.
I think it drops. We're just slowly.
Oh, yeah. Okay.
Yes, so they are, so CSAIL 10 and CSAIL 100, they differ in number of classes, and they differ in the type of images they contain. So the kind of matrices they are dealing with using these two data sets are different. So there are performance difference, not only the size. Thank you.
So what's referred to here as the learning process, is that sort of happening per matrix that I want to use in my multiplication, right?
Yeah, that's a good question. So I also should have mentioned that the speed up, the benchmarks are computing compute over the inference process. So the learning process is happens per matrix, and it's very slow. Yeah, it is very slow.
That kind of leads into another question. Because it's happening per matrix, the learning of these prototypes, could it be possible if I have a chain of multiple matrix computations, so let's say I want to do A times B times C, then maybe I can first do A times B, and then I know that I'm getting right, like a combination of those prototypes, and then when I have AB, I don't know if they mentioned this in the paper, but is it possible to then skip the like recomputation of the best prototypes, because I already know the prototypes of A and B, and I know that the resulting multiplied AB is kind of a combination of all of those prototypes.
So let me rephrase the question to see if I'm getting it correctly. So what we are saying is that we are looking, we should look at the training set, and we find similar products between those data points. So because we have encountered, say, this product, similar product before, we don't need to like do this hashing and selection again, and we just do this lookup directly. That's an interesting idea. Yeah, I don't think they are pruning the data sets. So yeah, they're computing on the whole, all the prototypes.
I was wondering what the size of such a lookup table will be if you want to get to good accuracy.
That's a good point, and that comes to my bit of a criticism of this work. Oops. Because in the whole paper, they haven't mentioned anything about the memory consumption, the memory overhead of this product table. So I haven't really got to measure that exact how big this prototype can be if we want to achieve high accuracy. But yeah, that's a good point. So yeah, so we come to the end of my presentation. So now let me do a little bit of nitpicking. I think the first assumption is quite strong, because I think nowadays it's no longer reasonable to assume that all the matrices and intermediate results can fit in a single device, especially for those large models like BERT. Right? And also, prior work has shown that most machine learning models, especially those heavy transformers, for example, they are memory bound. Retrieving values from memory is much more expensive than the compute. And also, after going through the proofs, I found the result is a little bit counterintuitive to me, because as that dimension of the training set gets smaller, the generalization bound gets looser. In my opinion, it should be the exact opposite. But having the theoretical guarantee is already a merit. So with that, thank you very much for your attention, and I'd like to take any further questions.
Okay, more questions, please.
I'm not sure if I understood that fully, but in the quantization at the beginning, we obviously did that with A transpose. Is there a reason for that, or why can we not just work with the rows of A?
That's a good point. So actually, they haven't mentioned. Sorry about this. Sorry about this. Bit font. Yes, this font is fine. They didn't talk about the reason exactly why we're doing this, but in my understanding is that the A matrix, if you can recall, is is n by d. So and in this paper, they assume that the dimension d is much larger than the embedding dimension d or another dimension. So what the quantization is actually doing is to compress the matrix column-wise, to reduce the dimension of d n. So I think that's probably the main reason why they are doing this. And also, this paper has quite different assumptions compared to other papers. That's why I haven't put. Thomas also has suggested me to put some theoretical bounds, but yeah, I think they have some bounds for the routines and overall approximation of the algorithm, but I think they have quite different assumptions as to what the dimensions, how large each dimensions is compared to other papers.
I also had a question on the size of the table. Because actually, when you asked the bottleneck question, I thought actually that memory is the bottleneck. But let me ask you, you said the learning is done for every matrix, right? For one matrix, you learn, you do the prototypes, and then multiplying by that matrix will become faster. Is that correct?
Sorry, yeah. Learning per matrix is for sparsity. It's for the sparse matrix multiplication. It's not, no. Learning per matrix is not for, is for the training set. So we have a training set for each matrix in the training set. We first learn, and we do the products. But for the test set, we're not learning anything. We just directly look up the table. Yeah.
But some of the learning process involves getting these prototypes, right?
Yeah.
And then you need to do the products of these prototypes, right?
Exactly.
To fill the table.
Exactly.
So what's the asymptotic runtime of that? I mean, that seems to me should be a lot larger than the matrix multiplication later, right? Of course, it's a one-time effort, but it's still larger, right? Because the way you showed it, you have a vector of length piece of 3, you do 8 prototypes, right? Then you have another 8 prototypes, and you compute all the products. So that's many more. So the pre-computation is a lot larger than the computation than a normal matrix multiplication, right? Is that correct?
That's true.
And do they quantify this? I mean, it should be easy to write down the formula of something.
So they have an approximation of this process, and I also wondered how the pre-computation compares with the actual matrix multiplication. And I was looking at this table. I think for each of the results, for each of the entry in this table, we need a more add operation. A multiply operation. So the pre-compute is to construct the lookup table. And I was thinking, if I remember correctly, the theoretical bound is NCK. So N is the number of rows, C is the number of prototypes, the subspaces, and K is the number of prototypes for each subspace. So essentially, we're iterating through all the entries to compute the prototype, assuming that each multiplication is constant. And I think why the pre-computation is worthwhile, is not that expensive. I think it's because of the quantization. So instead of doing this scalar, the scalar quantization that I talked before, we just do this linear projection. It's a non-linear project. It's a non-linear process where we compress the whole row, can be 100 some dimensions, to just a few prototypes, and each prototype can have a very small dimension. Although it can be, because for each subarray we have k prototypes, but together they should still be constantly bound if we do massive quantization in this case. But I haven't found very detailed memory limitation in the paper.
Has it been evaluated on what proportion of real life matrices this actually works? Because it takes into account that you have to have like matrices that come from the same distribution that you're looking from, and we don't usually know what is the distribution of the matrix we come from.
That's an excellent point, because I was thinking, I was also wondering why we can just do the lookup. I think there are, this is one of the implicit assumptions that's made. So they assume a machine learning setting, there's no covariance shape between the training set and the test set. So that's why they can do this safe lookup without recomputing anything. So they've trained on multiple data sets, popular data sets like Guttag 101, CFAR, and so forth. But yeah, I think they are assuming no distribution shift, because I saw in their code they are partitioning the same data set uniformly. So yeah, that's a good point.
When in the previous slides, when they have like 2-bit indices, do they do anything smart, or do they just use 2-bit numbers and use 32 bits unsigned integers for the lookup? Do they do reduced memory anyway?
No, they use 8-bit integers.
Okay.
For the indices. Yeah.
Another thing, in the results where you say exact, is it triple loop or plus?
Sorry.
Do they compare against that normal matrix multiplication or against plus?
A good point. Yes. So, the exact matrix multiplication, if I remember correctly, in their paper they said this is a modern implementation of the loss algorithm.
Okay. And one last thing.
Yeah.
Here it's inference on a model, but like I'm assuming it's a convolutional neural network that they took away, I don't know, some layers, and then they quantized those layers. Is this what they're doing?
Yes. So this is the loss layer, essentially.
Okay.
Yeah. They are taking the so-called activation, so a bunch of output from the previous layers from the neural network, say, and they are doing this product just for that approximation. So I think they're in the discussion section, they say, well, there might be further directions as to how we can implement those whole algorithms into deep neural networks.
Maybe you mentioned this and I missed it, but what are the dimensions of the matrices getting multiplied here? Are they 10 and 100, or like 10 to 0 to 10?
Good question.
Like, does the accuracy scale with dimension? As the dimension scale, does it degrade?
Okay, so I think there are two questions. The first one is how large the images are in this data set. The second question is, does this algorithm scale when we have larger images? Good questions. So I don't remember the exact number by heart, but the whole experience, in this experiment, the size of the input is the same.
Okay.
So they are not scaling any input size. As to whether the algorithm scales, I think they've mentioned in the paper that the algorithm scales pretty well because of the quantization, especially on large matrices. But I've got to double check on that.
Yeah, and then, I mean, as it goes on, then you're just going to be more bottlenecked by memory, right?
Yeah,
That's not
exactly.
really a question, but just.
Yeah.